Okay, good morning. So last time I talked about numerics of kinetic simulations of astrophysical plasmas, and I discussed the particle and cell method for simulating plasma physics on computers. Today I want to finish off a few things about actual implementation of particle and cell methods and special sauce that has to go into a successful particle and cell code. But then I want to spend most of my time actually on applications of particle and cell simulations to astrophysical examples. So last time we discussed two main types of particle and cell simulations, which were electrostatic codes and electromagnetic codes. And the two were applicable in different when different scales were of interest. For instance, if the domain you're considering and time scales you're considering are sufficiently, so the domain is sufficiently large and time scale is sufficiently slow that speed of light can be thought of as a very fast quantity, then you can apply electrostatic codes and solve Poisson equation on charge distributions and move particles according to the electric fields or static magnetic fields. If you're interested in a time-dependent problem where the speed of light is a fast quantity and particles can fly relativistically, then you have to use these electromagnetic codes. And in recent years, electromagnetic codes are really the ones that are doing most of the interesting science at the moment. So to remind you, what am I doing? Okay. To remind you, this is the main loop of a typical particle and cell code. We initialize the particles, initialize the fields if we need to, and then move the particles according to the equations of motion. In this case, it's a Lorentz force acting on particles. Then, given positions and momenta of particles, we can infer their charges and currents, and we discretize those charges and currents on a grid, and then use fairly standard methods for solving Maxwell's equations. So these come from electrical engineering. The finite difference time domain method is very successful in solving Maxwell's equations, and you basically convert from the charge density and current to electric and magnetic fields, and then interpolate them to particles locations. You got your force, and you continue the loop. So one important important property of these particle and cell codes, especially electromagnetic ones, is that you don't have to solve Poisson equation on every time step because if you're able to do that, then your computational expense simplifies, because then you don't have to use fast Fourier transforms or some sort of non-local communication across different subdomains in your simulation. So if you can avoid solving an elliptic equation, the better. And if you use a particular type of charge and current deposition called charge conservative current deposition, then you can actually avoid solving the Poisson equation. So you may think that this is that any method would actually give you charge conservation. It actually turns out to be not the case. So if you just take a particle and you know its velocity and you interpolate the instantaneous current to different parts of the grid, if you just do it, say, bilinearly in all directions, you will find that as a particle moves through the grid, you can then calculate what is the divergence of the electric field, which you compute. So the electric field you compute because there are currents associated with the particle motion. So if you just do a bilinear weighting, you will find that some of the charge got left behind. So the particle left the grid, but the charge was left behind. So that's not good. That accumulates and gives you horrible errors and can lead to an instability. So this charge conservative method actually works like this. It's sort of geometric. So if you think about a particle having a particular shape, say a cube, then as it moves through a three-dimensional grid, then different parts of that cube will intersect different faces of the grid as it passes through. And there may be a few if statements you have to program, because sometimes particle can go from one cell to another cell. Sometimes it can go through 3 cells at the same time, even in one time step, if it cuts the corner. So you have to be a little bit careful. So there are now fairly standard methods. One is by Villasenor and Buneman, and another more optimized method by Umeda in 2003, which works quite well. So you can deposit the current in such a way that the charge is actually conserved. OK, so a few things about actual codes that you can use. You always need boundary conditions, and the devil is usually in boundary conditions. So the good thing about these charge conservative codes is that they do everything right. The bad thing is that they do everything right, because if you think about a physical system like a plasma in the lab, it's really hard to set up a plasma without boundaries, right? It's really hard to have something infinite in the lab. It's really hard to drive a current through a plasma without having a source for that current and a sink for that current. So if you try to play on physical things with a particle in cell code, like you declare that suddenly you have a current everywhere in the plasma, or it just comes from the left wall, you will find that amazingly that left wall will charge up. And that current will fly away from the left wall until the wall charges up and the current comes back smashing into the wall. So you have to be, you have to think about the physics, and if the physics dictates that you have boundary conditions, you better implement those boundary conditions. So there are several techniques for implementing boundary conditions. The simplest one is the, let's see if I have it here. The simplest one is to put conductors on all walls. So a conductor on a wall means that the tangential electric field goes through 0. So you just declare that the tangential electric field along a boundary goes to 0, and that works quite well. It makes a nice conducting surface, and electromagnetic waves reflect off that surface. If you're interested in an open boundary, so some sort of an outgoing wave boundary condition, then the best game in town currently is what's called a perfectly matched layer by Bérenger in 1904. It introduces a kind of a funny material which has different permeability for electric and magnetic fields. So it's kind of an unphysical material, but it has this wonderful property that it matches very well to an outgoing electromagnetic wave. So it has a very minimal reflectance from the boundaries. Another type of boundary condition that's been useful is what's known as a moving window. So if you have something fast moving through a grid, for instance, a relativistic beam moving through the grid, then you would be forced to extend your domain if the beam is moving, if you're interested in long-term integration. Another alternative is to actually move your domain together with the beam. And if you move it at a kinematic speed of light, so basically you say that after a few time steps, you just shift everything back by the speed of light times this number of time steps, then your causality is not violated. Your the stuff that you have to inject on the right side of the domain is pristine and fresh. There is no communication faster than the speed of light, so that it shouldn't be affected by whatever is going on in your box. So you can have this moving window when you fly with the simulation, with the beam in your code. OK, so the particles can be created and destroyed in the box. If you have to be careful, though, if you're not solving the Poisson equation, so if you're solving this, if you're using this charge conservative current deposition, then you better not introduce one sign of charge arbitrarily. So if you just say that I just created a positron over here, then if you didn't solve the Poisson equation to introduce electric fields associated with that extra charge, the code will assume that there is a negative charge sitting in the same place that compensates all the fields around it. So even though you just introduced one particle, you really introduced two. And that second particle with a negative charge will be left behind sitting on the grid. As the mobile particle leaves, this presumed static particle just is left behind. So you have to be careful about that. So what you want to do is introduce charges in pairs, so an ion and an electron together, if you're not solving the Poisson equation. If you are, then that's another story. OK, so a few words about parallelization. The best technique so far we've used is just domain decomposition. And the way you slice your domain depends on the particular simulation, particular setup you're interested in. In the case of shock simulations that I will show you, we mainly we have one direction along which we do not distribute domain across processors, and we have another dimension where we or another 2 dimensions where we slice the domain and distribute it to different processors. So the way you slice depends on the symmetries of your problem. OK, so a few words about optimization. We are, in general, pushing billions of particles. So in order to have a good 3-dimensional simulation, you end up pushing billions and billions of particles, so that's very expensive. And the better you can optimize your code, the better the payoff is. And the main time expense in these codes is really twofold. So there is the mover, which includes the interpolation of the electromagnetic fields to the particle and the push of the Lorentz force, and then the deposition, where the particle's current is calculated and assigned onto the grid. So typically, these 2 steps take about the same amount of time in a large simulation. And it's kind of strange, because this part actually computes some, there is a lot of floating points. So you actually use some multiplications and adds. Whereas in the deposition, you basically just take a number, just a few floating points, really not a lot, and then you just put it into memory. But the reason why these 2 are taking almost the same time is because these codes are typically not CPU limited. They're limited by the communication to memory. So you have a few billions of particles in your memory, and in order to move these particles, you need to take them down to your cache. And if you're not careful about either ordering or reordering your particles, if you have cache misses, or you have to address particles in different parts of the domain in one time step, you will lose performance significantly. And so you want to be optimized in terms of the memory access. And Kevin Bowers will give a talk on Thursday where he'll talk about it in much more detail. Also, I hope he will talk about this thing about single versus double precision. Since we're memory limited, we're better off with a single precision code. So it takes half as much memory, and it's really faster. The trade-off is not doing stupid things. So you have to be careful in how you use single precision, because there is only limited amount of precision in there. So if you can't, you have to be careful in how big your grid is, for example. If your grid is larger than 64,000 cells, the precision of your position, if you're just recording position as a full floating point number, the precision of your position on the right side of the grid will be different from the precision of position on the left side of the grid. So that's kind of unfortunate. So there are tricks of dealing with it, and Kevin will talk about it in more detail on Thursday. OK, so a few notes on these particle and cell methods. There is no, the good thing about them is that there is no subscale physics. So typically, when we talk about Hydra simulations or MHD simulations, we always have this genie that lives on the smallest scales, that takes care of the viscosity, resistivity, and so forth. There is no genie here. This is the smallest scale you can have in the plasma. You don't have much happening below the skin depths of the plasma, and we actually resolve that scale. So that's a good thing. The bad thing, conversely, is that if you want to do a macroscopic problem, you're stuck resolving all these smallest scales. So you have to be careful in choosing your problems. So Another thing is, I was asked whether AMR is a good idea for particle and cell codes. In principle, yes, but in practice, in most of the things I've tried, AMR makes little difference, mainly because we're resolving fairly small scales, and if your plasma is really clumped on those small scales, you have something else going on. So most of the problems I've dealt with are fairly isotropic, and they don't involve considerable clumping in places. If you think of these PIC codes are basically particle mesh codes, then the difference with gravitational particle mesh is that we have two signs of charge. So we not only have attractive forces, we also have repulsive forces. So that's why there is no gravitational collapse, and these plasmas don't form very sharp spikes in density. Another note on the PIC codes is that this finite different time domain method for solving Maxwell's equations actually conserved the divergence of B to the machine precision, so that's good. The downsides of PIC is that there is particle discretization error, so we introduce macroparticles, and there isn't going to be as many macroparticles as there are particles in the plasma, never. So you're going to introduce some discretization error. The particles will be finite size, and there will be statistical noise to these due to these particles. And if you under-resolve the grid, you may get grid aliasing and additional noise, and so forth. So absence of short-range forces is either a good thing or a bad thing, depending on what kind of problem you do. When we try to do collisionless plasmas, it's actually a blessing. But actually, if you don't have enough particles in the simulation, then the statistical noise and the particle discretization error will actually introduce short-range forces for your simulation. So you can actually have collisions even though you didn't plan for them. So just these random fluctuations due to discrete particles, if you don't have enough particles, in other words, the number of particles in a Debye sphere is small, then you introduce collisions back. So you have to be careful on that. Finally, if you're running billions of particles, it's not always obvious what to do with them, as Volker mentioned. But really, there isn't an alternative. The alternative for simulating these kinds of plasmas is solving six-dimensional Vlasov equation. And so far, this has not led to significant advances. OK, so let me go on with the applications. So last time, I showed you the simulation of the laser-plasma interaction. So this is not an astrophysical application, but this is what these PIC codes are used for in the laboratory. So we have here an electron beam propagating through plasma, exciting an electrostatic field behind it. So this is the shape of the electrostatic field. And a particle riding on this field can get accelerated. And this is a potential for producing laser plasma accelerators with large gradients of acceleration potential, but accelerating electric fields. But it's happening basically inside of your small-scale laser plasma interaction. So this is a Nature paper from an experiment at SLAC, where a simulation was confronted with an actual experiment, and the two agreed to remarkable precision. OK, so other examples, these codes are commonly used in engineering, where you have, say, various gas discharges. If you want to simulate a fluorescent light bulb, for example, or you want to deal with plasma processing. So you have a wafer, you want to deposit a film of plasma on top of it, or you want to etch something on a wafer with plasma. So these kinds of methods are used for in industry quite often. Here's a simulation of a lightning interacting with a gas tank. So you drive a strong current through the, presumably through, which is a lighting, and then you look at what electric fields accumulate on the edges of your gas tank. And if there's above a certain value, you may get a discharge and you ignite your gas tank. So all of this is fine and interesting, but we're here for astrophysics. So, so what are typical environments where we encounter plasma physical issues that need to be addressed with this type of simulations? Basically, it's in any problem where you have a non-trivial distribution function. So what I mean by that is if your distribution function is multi-valued, that means that you, in a given point in space, you don't have just a single velocity. Your fluid is not just moving left or right. You may have counter-streaming. You may have fluid going both left and right in the same place. And that's a very common thing in plasma. So an MHD moment or a hydro moment will tell you that fluid is not going anywhere. Yet there is a lot of free energy in counter-streaming. And that counter-streaming can lead to instabilities and energy exchange. So for example, in the homework problem, you looked at the example of two-stream instability, where this was an electrostatic two-stream instability. So this is the velocity space versus the x-coordinate. So here I have a beam of electrons going to the right, and here a beam of electrons going to the left. This is the velocity in the x direction. And if you run it, you see that there are oscillations developing in both of these beams. Basically, they interact with each other through electrostatic fields. Some parts of the beam are slowed down, some are accelerated due to the electric fields. And what you find is that you're tapping this energy of counter-streaming into generation of electrostatic fields. And those fields slow down the beams, and you reach a resonant condition where you start seeing these formation of the loops or holes, electron holes in the momentum space. So this is a typical nonlinear development of a streaming instability. Okay.
The beam instability is fastest on the largest scale. Why it's growing fastest on relatively small scale?
The fastest growing scale has to do with the velocity of the beam and the plasma oscillation. So this is an electrostatic instability. So you have to be in resonance with. So when you're moving, when you excite the oscillation in the beam, it moves with the beam, right? So if a particle on the other side sees that sees these oscillations in resonance, it will start decelerating and accelerating. So that's essentially, so the typical wavelengths here is given by the velocity of the drift and the plasma frequency. Okay, so let's go back. So examples where these kinds of distributions are commonly encountered are collisionless shocks, where you have two fluids trying to collide with each other without having strong Coulomb interactions, Coulomb collisions. Then important question that can be addressed with this particle and cell method is where particle acceleration happens in astrophysics. So these are some particles out of a thermal equilibrium are taking to highest energies, and it's really hard to describe this in a continuum way. So it's just some small subset of particles for some reason are given extra energy, and we can understand how that happens by actually studying the plasma physics of it. Next is propagation of cosmic rays and associated generation of magnetic fields as cosmic rays propagate through the interstellar medium. Then there are questions related to reconnection, the speed of the reconnection, and the physics that governs the rate of the reconnection. And finally, the ultimate dissipation of turbulence. So if you have a turbulent cascade, eventually it goes to the resistive scale, and where that energy finally ends up, whether it goes into electrons or ions, is not really understood at the moment. Okay, so let me show you a few case studies. So here is an example of a simulation we did where we're considering what happens in the interaction of two pulsar winds. So there is a interesting double pulsar binary where you have two pulsars orbiting each other. One is a one is a millisecond pulsar, so this blue guy is the faster pulsar, and then another one is a normal 2.5 second pulsar. And as you can see, both of those beams intersect your line of sight once in a while. And the two periods are not to scale. But the basic idea is that this pulsar, this faster pulsar, is emitting a wind of particles, wind of electrons and positrons, which are impacting the magnetosphere of the slower one. And the balance of forces is such that the pressure of the wind from one pulsar is severely affecting the shape of the magnetosphere of another pulsar. So essentially, you have an interaction sort of like between the solar wind and the Earth magnetosphere. So if this is the magnetosphere of one pulsar, then there is a pressure of the wind from another one, and it distorts the shape of the interaction region. And so we simulated this using the particle and cell code. So what's shown here is the slice through a three-dimensional simulation. Here, the lines show the magnetic field, and you have an incoming flow from the faster pulsar. This is going to simulate the slower one. So what we did here is we inflated a dipole inside of the moving plasma. So we basically turned on a current loop inside of the simulation, and that inflated a vacuum magnetic field. And then the particles from the incoming wind had to interact with this new magnetic field. And there are two types of interactions you can have. One is when the field in the wind is aligned with the field on the side of the magnetosphere, and another when it's not aligned. So in this case, you can get reconnection, and in this case, you don't get reconnection. So it's sort of like the day side and the night side physics of the Earth magnetosphere. So here is a movie of what it looks like. So we can have this dipole rotating, and what we find is that there is a shock that's created around this magnetosphere, and the shape of that shock is oscillating depending on which phase this pulsar is in. So on one side, you get reconnection right here, and then on this side, you don't get reconnection, and so forth. So
what is controlling the amount of reconnection that is taking place?
Right. So to some degree, the reconnection here is done correctly. So we're actually resolving all the scales needed for the reconnection. On the other hand, we're not. The scale of the reconnection region is kind of comparable to the size of the magnetosphere. So that will not be very realistic. What I want to mention here is that I'm using a particle and cell code on a problem where I would have been better off with an MHD code. So there is really not much point in using particle and cell code in this case. The reason I wanted to demonstrate this is because just to show you that on large enough scales, the particle and cell code actually reduces to an MHD code. It's going to be a very expensive and sometimes diffusive MHD code, but it actually, on large scales, it reproduces the MHD physics. So what controls when you actually go towards MHD? Basically, the size of your obstacle here has to be many tenths of skin depths. So if the size of this obstacle was comparable to a few skin depths, you wouldn't get this nice structure. You would get plasma oscillations and large fluctuations in density on that scale. But if your object is fairly large and the plasma scale is sufficiently small, then you start to reduce your simulation towards something that MHD would produce. OK, here are few more visualizations of this type of interaction. So here are the three-dimensional cuts through this problem. So you can see a bow shock forming in 3 dimensions, and that bow shock is oscillating. And there is a particular signal that actually is inferred in this double pulsar binary that has to do with this reconnection that happens in the bow shock of the pulsar. So let me see what happened here. Oops. Okay, never mind. So this is a kind of volume rendering of what the density of the bow shock looks like around this structure. Okay, so another example where collisionless physics is needed is actually studying the inner structure of these shocks. So this is actually doing this kind of a simulation is what started me in thinking about what is the physics that happens at this red zone, where the density seems to increase and the magnetic field is also increasing. So this is where the shock is actually happening. So what I wanted to understand is how do these shocks actually work? And the interesting thing about astrophysical shocks is that they are fundamentally collisionless structures. So what I mean by that is that a typical shock in the air, for instance, is mediated by the collisions between molecules of air. And the mean free path in air is basically a micron. So if you have some bullet flying through the air, this sharp shock is mediated on the scales of a few microns. In astrophysics, we don't have that luxury. And the typical mean free path can be comparable or larger than scales of interest of your problem. So for example, here is a supernova remnant, and it's expanding, and you can see a very nice shock surrounding this supernova remnant. And if you ask what is the mean free path of particles in here, you will find that it can be up to 1,000 parsecs. Whereas the size of this thing is about a few parsecs. So obviously something else is taking place here that makes possible for such sharp structures and shocks to be created. In galaxy clusters, if canonical mean free path would be comparable to the size of the galaxy cluster. There are arguments whether this is the defining figure of merit, but nevertheless, that's the answer. So this is the typical scale of the Coulomb interaction. So it scales with temperature and inversely proportional to the density. And this number is fairly large in most astrophysical scenarios. So these collisionless shocks appear in many environments, ranging from the solar wind to supernova remnants to pulsar wind nebulae, which are the relativistic winds inflated by pulsars inside of supernova remnants. We also find them in gamma ray bursts, in AGN jets, and they really span a large range of parameters going from non-relativistic to relativistic flows. They also span a large range of magnetizations, meaning the environments in which they propagate have different types of magnetic fields from small to large. And one way to show this is using this type of a diagram where on this axis I'm plotting the for velocity of a shock. So this is gamma of a shock times v over c of the shock. And it goes from non-relativistic ones, 10 to the minus 4 here, up to mildly relativistic ones to fairly relativistic ones. And these acronyms here, so this is the solar wind shocks, supernova remnants. These are the shocks during the formation of structure, during the accretion onto clusters, for example. These are the active galactic nuclei jets, pulsar wind nebula, gamma ray bursts. And so what's shown here is we know fairly well how fast these shocks are moving. We don't know that well what are the typical magnetic fields that they're encountering. So there is a relatively large range of magnetic fields that you can find here. The solar wind shocks turn out to be the most magnetized and the slowest ones. So why is this interesting? The reason is that most of these flows seem to display very similar properties. So most of these shocks seem to be able to do three things fairly well. So they seem to be able to accelerate particles and create power law spectra like these. They also seem to be able to amplify magnetic fields, either creating them from scratch if there are no magnetic fields to begin with, or significantly amplifying pre-existing magnetic fields. And they also, in some cases, manage to fairly efficiently exchange energy between ions and electrons in a flow. So here is, let's see. Here is an example of supernova remnant Cassiopeia A, where you see this. This is a, I think, 7-year movie, and you can see here these thin rims surrounding this supernova remnant, and this emission is synchrotron, and so presumably there are particles accelerated in this shocks. And if you look at the spectrum, it looks like there is a thermal bremsstrahlung component plus a non-thermal tail. And this tail is quite prominent. And it tells you that electrons are accelerated in these shocks. Also, evidence from dynamical shape of these, of the position of the forward and reverse shock in some of these supernova remnants tells you that also cosmic rays are accelerated in shocks. So about maybe 10% of energy of these shocks can go into acceleration of protons. Okay, so how does the acceleration happen? The original idea goes all the way back to Fermi, where he reasoned that scattering of moving clouds could lead to effective acceleration. And it turns out that moving clouds can both approach each other and recede from each other, so that gives you a less efficient mechanism than actually scattering around shocks, as was pointed out in the late 70s. So in a shock, you have this is the upstream flow incoming into the shock, and this is flow going away from the shock. And they're basically two converging flows, no matter from which frame you look. From this frame, this flow is approaching. From this frame, this flow is not receding as fast as this one. So basically, you have these two converging walls, and if you have two tennis players trying to knock the ball backwards and forwards, obviously the ball's energy will increase. And that's essentially what happens in a typical shock acceleration scenario. There is one problem, though. That problem is what is actually working as these rackets? What is providing the scattering? And that scattering is thought to be provided by magnetic turbulence generated near shocks. That turbulence could be either pre-existing or self-generated by particles that are being accelerated at the shock. So this efficient scattering is extremely important, and all of the analytic studies and studies of test particle diffusion around shocks emphasize that you need large amount of turbulence in order to have this efficient acceleration happen. And we really don't understand how this turbulence comes about. One way to explicitly address it is by simulating a shock, a collisionless shock with ab initio plasma simulation, and then seeing what kind of turbulence you create, and if that turbulence actually can accelerate particles. So that's essentially what we tried to do. So the idea is to somehow excite a shock in the simulation. And there are several ways of doing it. The simplest way you may think about is to just take two shells or two clouds of plasma and slam them into each other. So if you had no Coulomb collisions, you may think that these two clouds may just pass through each other, right? Except, as you saw, that would be that's an intrinsically counter-streaming configuration. So there is free energy there to be tapped. And if that free energy can be tapped by some plasma processes, you can actually slow down the flows. Once you slow down the flows, you will get something that MHD predicts. You will get a contact discontinuity, and you will have two shocks, one propagating into that flow, one propagating into that flow. And the compression on the shock should be just what MHD tells you, because MHD just tells you about conservation laws. And no plasma physics violates conservation laws, thank God. MHD will not be able to resolve this transition. It will just tell you that it's a very sharp jump. Using plasma physics, we will actually be able to resolve this transition and see if this configuration actually ever happens. So as you can see from symmetry here, we could replace this other flow with a mirror. So if we put a wall here, which is a reflecting wall, then the problem will be basically identical. So if these particles start to reflect off the wall, eventually there will be compression, and the shock will propagate. If it can be created, the shock will be propagating through the grid here. OK, so what we do is we set up shocks like this. We have a wall. We have an approaching flow. I'll show you just relativistic simulation. So in the relativistic case, we're typically assuming that the flow has a gamma of about 15, Lorentz factor 15. That's fairly large. So we're not in the trans-relativistic regime. And then when it slams into the wall, you get a compression that propagates through the domain. We can also add the magnetic field. So we can also add the variables, the strength and the direction of the magnetic field. And that will be part of the results. So what determines the physics of these shocks? And it turns out that there is one important dimensionless number, which is the ratio of the magnetic energy to the kinetic energy in the flow. And this has to do with, it can be phrased as an inverse Mach number of the flow. The smaller this ratio, the smaller is the magnetic energy compared to the kinetic energy, the larger is the Mach number, the Alfvénic Mach number of the flow. And it turns out that depending on how big is the Mach number, how big is this magnetization, you can switch between two types of shocks. Shocks that are mediated by magnetic reflection and shocks that are mediated by instabilities or streaming instabilities between plasmas. So here are two typical examples of what these shocks look like. So this is a shock for a moderate magnetization. And this is what's shown here is the density. And this is the direction of the magnetic field in the upstream. So the flow comes in like this. And then there is a fairly sharp transition into the downstream. So there is a jump in density and slowdown in the velocity. And the scale is typically 1 Larmor radius of a particle. On the other hand, there are shocks which look more like filamentary shocks, where the transition is not as sharp. It still is microscopic on large scales, but the transition happens on many skin depths of the plasma. And this transition is essentially due to an instability, due to filamentation instability. So here's what a shock like that looks like when it's forming. So there was a wall over there. The flow came in. And you can see a compression propagating through the box. And there is filaments of density in front of this shock. So why is this shock working? It's working because there's generation of magnetic fields. So initially, this flow had no magnetic fields. And so I collided with a wall. And then returning particles here were counterstreaming. And that counterstreaming was free energy that could be tapped. And it was tapped into creation of transverse magnetic fields. So there is a particular instability called the Weibull instability that takes the free energy of the counterstreaming and forms loops of magnetic fields. And you can see that those loops start on small scale, and then they grow to larger and larger scales. And these transverse magnetic fields can deflect particles. And that deflection slows down the flow. So the main flow comes in like this and decelerates in the background behind the shock. So if you
first realized, by the way?
Sorry, what?
When was Weibull instability first realized?
Weibull 53 or something? Yeah. The original instability was mainly for temperature anisotropy. So if you just have an isotropic gas with temperature transverse dimension different from the temperature in the longitudinal direction, they will equilibrate due to the creation of these transverse magnetic fields. And this similar idea, if you just have two cold flows going through each other, you get the same thing. So this is the profile of density through such a shock. And other than this transition, if you go far enough that way, far enough this way, you will get jump conditions given to you by hydrodynamics or MHD. So what we're actually resolving is this transition over here. And this transition is mediated by magnetic fields. The magnetic fields are transiently appearing. This is the magnetic field energy. It appears in the middle of the shock, and then it decays in the downstream. So these magnetic fields came up when they needed to be to stop the flow. And then when this flow has decelerated, the magnetic fields start to disappear. The physics of the instability is quite simple. If you imagine electrons from both sides. So these are electrons going left, and these are electrons going right. And imagine a magnetic field fluctuation in the transfer direction. These red arrows are magnetic fields transversely to the flow. Then what will happen is that the left-going electrons will try to coalesce towards the zero of the magnetic field, and the right-going electrons will be deflected away from that location, right? So next to the zero of the magnetic field, you will have a net motion of electrons that way or a current in that direction. Okay, and that current is exactly what's needed to amplify this magnetic perturbation. So that's an instability, right? So there is, by separating the plasma, by initially have a charge and current neutral plasma, but small fluctuation of the magnetic field can separate them, create currents in a local direction, in a locally enhancement of current, and that amplifies the magnetic field even more.
How do you figure out what is the mean number of particles that you need?
Sorry, what?
How do you figure out what is the mean number of particles that you need to get this from? Then the physics.
Okay, so the typical scale of the instability is actually the skin depths of the plasma. So if you resolve the skin depths and you resolve the plasma frequency, this instability will appear. So that's what's good about this instability in plasma simulation, because we're forced to resolve these lengths. And this instability happens to be on this length. So this is a good fit. If this was a very long scale instability, we would be in trouble. But thankfully, that's exactly the instability that mediates these types of shocks. OK, so let me show you. I mean, you will get noise if you under-resolve in terms of putting too few particles. You will get noise in your simulation. But the growth is basically very robust. OK, so let me show you how this shock looks like in more detail. This is a two-dimensional simulation now on a much larger scale. So what's happening here, there are a lot of things happening at the same time, so I'll explain them. So I'm injecting relativistic flow over here, and there was a wall over there. And this is the density through the shock. And what you can see is that the shock forms, so the compression and density forms, and it propagates through the flow. This is an integrated density profile. So there's a jump, and this jump satisfies the jump conditions of hydrodynamics, or MHD. This is the magnetic energy that's being created. And as you can see, the peak of the magnetic energy is right in the middle here. And this is the shape of the magnetic filaments in two dimensions. So you can see that there are filaments in the upstream, then they coalesce, and then they form these islands in the downstream. And in 3 dimensions, these islands are foot points of loops. So these are 3-dimensional loops that are crossing this 2-dimensional box.
What is the mass ratio in this?
Right, thank you. So this particular simulation is mass ratio 1. So this is electron-positron plasma. I'll show you electron-ion plasmas in a few slides. OK, so initially there was no magnetic field, but the magnetic field got created just due to this interaction. And so there are lots of interesting things here. There are tangled filaments. There's downstream field. There are waves that are propagating in front of the shock. This is a subject of a whole other lecture. What I wanted to show you here, this is a 3-dimensional simulation. And what we're doing is we're flying through the box. And this is density profile. And this is the magnetic energy in a slice transversed to the direction of flight. So as we get closer and closer to the shock, you see that there are loops of magnetic field that form. So this is the energy of magnetic field is increasing here. There are these loops of magnetic field that form. And as you get closer and closer to the shock, there are smaller types of loops that appear. And all of this can be understood in terms of the counter-streaming. So the density of two counter-streaming beams is changing as you get closer and closer to the shock. And what happens is that there are particles actually reflected from the shock going back towards the upstream. And that counter-streaming is what's producing these types of magnetic field fluctuations and loops. This is what it looks like in 3D. This is magnetic energy. So you can see these upstream filaments. In cross-section, they look like these merging loops. So here you see the immediate problem. This is rich physics, right? So you get these three-dimensional simulations. Something is happening, but you have no way of understanding what happened. So you need to, I cannot understress the importance of, or overstress, the importance of visualization and importance of actually being able to look at your data. Because this is a lot of, hundreds of gigabytes of stuff sitting on your disk. If you have no way of looking at it, you can't do anything. So, okay, this is just an example of these types of counter-streaming instabilities. Here, the flow is going through the simulation plane, and what you're seeing here is the magnetic energy. And so here it is again. If I change the density contrast, so if one beam is more dense than the other beam, then you can see that the type of the filamentation changes. So now you get these more confined loops, right? And if you change the contrast even more, so the one beam is much denser than the other beam, you get these types of loops. If you run it in reverse, it looks like cell division in biology. But this is another PITP school. So, okay, so let me show you what kind of diagnostics we get and how we learn of what happened in this simulation. So, in principle, all the information is there. We have a few billion particles, and we could, if we force ourselves, we can output trajectories of a few billion particles. Good luck looking at them. You look at one particle, and it's one particle. You don't learn much, except in some rare cases. So in some rare cases, they can actually, by looking at trajectories of particles, we can learn something. So here is what's shown in the background is the color is the magnetic energy through the shock. So you can see filaments over here and the islands of magnetic field downstream. And here, what I'm showing are pieces of trajectories of each particle, or few test particles. So the yellow ones are electrons, the red ones are positrons. And you can see that most of them are moving in straight lines in the upstream. And then they get deflected at this shock. They get deflected by a strong field in the transition. And then they're basically random walking around. And if I just showed you these trajectories of these particles, you would say that this isn't just a collisional gas. They seem to be colliding with something. And that something is the islands of magnetic field here. Now, notice that some particles, like this guy or that guy or this one, are moving in the wrong direction. So there are some particles that are going towards the upstream from the shock. And not only are they going towards the upstream, some of them are also going sideways. So you notice these particles quite immediately, and then you ask, what's happening here? And what's happening is that the shock is, the reason why the shock is existing is because it maintains the counter-streaming. So what's shown here is a phase space. So this is the momentum space. This is x direction. This is the velocity. And this is the incoming stream. It has negative momentum. It's going towards the shock, and then it isotropizes in the shock. And what you see here are the returning particles. This is a particle with positive momentum going towards the upstream. So there is a significant fraction of particles that are reflected from the shock, sent back, and this counter-streaming is what's producing the instability that's supporting the shock propagation. So this is an intrinsically counter-streaming distribution, which you can't simulate with anything but a kinetic method.
Question.
Yeah.
I saw one particle which seemed to be bouncing down the collision, so it's moving, so it's in the stream area that it was bouncing.
bouncing. This one? Okay, so there are magnetic fields. So these colored areas are magnetic energy. So a particle gets deflected in the magnetic field, and so it's deflected, it's trapped between these two islands of magnetic field, and it's moving towards the shock. So it's just the Lorentz force doing that in the E cross B drift. Okay, so what's interesting is that if you now measure the spectrum of these particles in the downstream, so you measure the spectrum behind the shock, what you find is that there is a broad Maxwellian distribution with the peak energy of this Maxwellian given by the kinetic energy of the incoming flow, which was gamma 15 in this case. So this peak, basically, most of your flow just isotropized in the downstream, as it should. But then you see a tail. And this tail is fit by a power law with an exponential cutoff. And with time, this exponential cutoff is increasing to higher and higher energies. So what we see here is that these ab initio simulations are producing accelerated particles from scratch. So I didn't put any magnetic fields. I didn't put any accelerated particles to begin with. And they just appeared from the intrinsic turbulence in the simulation. So the typical numbers I get here is that the slope of the distribution is minus 2.4, which is a reasonable number for astrophysical applications. These particles are only 1% by number in this tail, but they carry about 10% of energy. So that's very important because this 10% of energy can actually start modifying your shock. So here is an example of an accelerated particle. So we could, the way we get this is what I'm going to show you is a trajectory of a particle that reached one of the highest energies in the simulation. And the way we do this is, the simulation has, let's say, 5 billion particles. Initially, you don't know which one of them will get accelerated, right? So somehow you need to select that one lucky particle and plot its trajectory. You can't plot the trajectories of all 5 billion particles. The disk will overflow. So what we do here is we actually run the simulation twice. So we run it once, we figure out which particle got accelerated, and then hoping that your code is reproducible, you can run it again, and you will get that trajectory. So actually, our code was not reproducible for a few months. It was quite agonizing, but it worked. I mean, actually, with days, basically, right. So we use about 200 processors. It will take a few days to run. Yeah, depends how long. I mean, our domain is actually expanding with time, so we can run in principle longer and longer and longer if you have enough computer. Okay, so what you see here is the magnetic islands here, so magnetic filaments, and this is the trajectory of a particle, and the blob on the particle the size of it corresponds to its gamma. So it's going to grow as the particle gets accelerated. This is the gamma plot versus time. So you can see that the gamma is not changing over here, but then it's not going to cross the shock, and the gamma has increased, and it's going to cross the shock again, and the gamma is increasing another time. So basically, this particle is hugging the shock, and every time it goes back and forth, you get a kick, and that gives the particle more energy. So the claim here is that this is the diffusive shock acceleration at work. So this, the Fermi process applied to shocks is actually possible to have in a self-consistent way. What's making this particle gain energy are these magnetic turbulence that is generated. And this magnetic turbulence is generated by the particle reflected from the shock. So it's a case of a bootstrap. So the particles create the turbulence that accelerates some fraction of the particles. Okay? Here is, let's see.
I have a question.
Yes?
How does the energy done to this non-thermal tail depend on Mach number?
Very good question. So this is a relativistic shock. So for anything we've tried with gamma larger than 5, let's say, and in no initial magnetic field, there is no difference in what we see. So the whole spectrum just shifts with respect to your mean gamma, but we haven't seen the slope or the efficiency change. Now the story is completely different if you go non-relativistic shocks. There the Mach number is very important, and this is an active area of research right now. We don't quite, there are several mechanisms at work as well, so we don't quite have the answer for that yet. Okay, let me just show you a few more examples of how these types of simulations work. So this is again, this unmagnetized simulation. What's shown on this slice is the magnetic energy, and on this slice is the density, and this slice is the magnetic energy again. So you see these loops. So now what I'm going to do is I'm going to change the background magnetic field. Initially, there was no magnetic field here. Now I'm going to start adding the background magnetic field. And so I'm adding a field like that. And what you see here is that there's still filamentation. So there's still filaments, but those filaments now look like they're not loops anymore. They're more like pancakes. And so they get flattened by this presence of the magnetic field. The reason being is that it's easy for particles to filament and move along the magnetic field, but it's harder for them to filament moving sideways to the magnetic field. So this filamentation changes its nature. Finally, if you go to even stronger magnetic field, so now it's 10% of energy in the magnetic field, then you see that this filamentation is largely gone, and the shock structure looks quite different. It's no longer filamentary shock, it's this magnetic reflection shock. So basically particles coming in are now making a Larmor gyration, and inside of that Larmor gyration they almost never go back very far and continue on to the downstream. So we've studied this now that we know that these shocks can accelerate particles. We studied the spectra depending on the magnetic inclination angle. So if you introduce a background magnetic field and change the magnetic inclination angle, what you find is that the efficiency of acceleration actually depends on the angle. It doesn't depend so much on the strength of the field, but it does depend on the angle at which the field is oriented with respect to the flow. So this is 0 degrees, which means along the normal to the shock. 15 degrees, slightly more inclined, 30 degrees. And then what's interesting is that beyond certain angle, the efficiency just drops to 0. You basically reduce back to the Maxwellian. And one way to understand what happened here is the following, that these are relativistic shocks. That means that the shock is moving at a healthy fraction of the speed of light. And beyond a certain angle of inclination, a particle trying to stream in front of the shock, even moving at the speed of light, would have a hard time outrunning a relativistic shock. So you run into the causality problem, and the shocks with a larger angle than certain value, which is about 34 degrees in this case, the shocks with larger inclination angle would be what's called superluminal, which means a particle has to move faster than the speed of light along the field in order to go into the upstream. And the crossing of the shock was essential to giving you acceleration, and that's why the shocks at higher angle than about 32 or 34 show almost no non-thermal acceleration over here. So immediately, these kind of simulations give you important constraints on the type of geometry and strength of the magnetic field you should have in relativistic shocks. So if you, say, have a gamma ray burst or an AGN jet, and the model tells you that you have to have a transverse magnetic field and it should be sufficiently strong, I will tell you that it's very hard to accelerate particles in that case. Yeah, what's up? Sorry.
Does the magnetic field that's generated in the shock move with the shock? What's the rest frame of the field?
The generated field, or the generated field? It's not moving in the downstream frame. So it's frozen into the downstream plasma. So the field is advected with the incoming flow, and then it's frozen into the downstream plasma. Okay. So the filaments are moving with the shock, but a magnetic filament is not something that the particles are still streaming through it. It's not a structure that's fixed on the shock, basically. It's oscillating and changing in time. But on average, they're staying with the shock. OK, let me skip this. OK, so let me show you an example of an electron-ion shock. So this is, we've explored mass ratios from 16 to 1,000. I think this simulation is about 100. So what you're seeing here is, again, injection at relativistic speed. This is the density. This is the magnetic energy. And this is the density profile. The unit of measurement here is the electron skin depth. What's important for the structure of the shock is the ion skin depth. So the ion skin depth is square root of mass ratio larger than electron skin depth. And what you see here that the shock indeed forms. It takes a longer time to form, but again, the filamentation, this Weibull instability, but now driven by the ion Weibull instability, is what's mediating the shock here. There was no initial magnetic field. And we're now doing the same experiments with adding magnetic field for the electron-ion case. And basically, it reproduces a lot of the results from the pair simulations. There is some differences in efficiency of acceleration and so forth. OK, so
question, is there any prescription for synchrotron radiation?
It's a very interesting question. So there is no synchrotron radiation included in this simulation. So if you ask what is the cooling time of particles, it's quite long compared to the simulation. So it shouldn't be important for the structure of the shock in most cases, except for some extreme cases in prompt GRBs. But there is some radiation included in the simulation by the fact that we're moving particles and charged particles and solving the electromagnetic equations. So the low frequency cyclotron radiation, for instance, is included in the simulation. What's not included is the high frequency synchrotron radiation. So when we resolve the Larmor radius, that type of radiation with that type of wavelengths is included in the code.
But if this 10% of very energetic particles play important role in this precursor, well, maybe it is important the synchrotron radiation is important to include in the precursor structure of the different.
You mean energetic?
Yeah, I agree that for thermal particles, the synchrotron radiation is unimportant, but for very few energetic particles, it might be important. And
Yeah, they are propagating in much weaker magnetic fields. So I agree that you can find some parameters where this is an important question. And we actually have a paper about this where we include radiation in the precursor. And what happens that the shock is spreading out, it going to a larger scale. So but it is a good point. It's just it doesn't always apply in all astrophysical environments. You can find some examples where this is important. OK, so just wanted to mention a few things about these electron-ion shocks. So one interesting thing that we find is that there is a very efficient energy exchange between ions and electrons. So what's shown here is the energy in the flow. Initially, all of the energy is in the ions, because if you have electrons and protons moving with the same velocity, the ions are obviously much more massive, so their kinetic energy is much larger. So all of the energy of the flow was in the ions, and almost nothing in electrons. And then, as they go through the shock, you can see ions lose 20 or 30% of energy, and all of that energy goes into the electrons. So the electrons warm up to almost equipartition with the ions. And that happens in these filamentary structures as electrons move in and out of ion filaments. So the actual microphysics of this process we still don't quite understand. Mainly that it's very hard to analyze these simulations and ask what happens to the bulk of the flow. You can ask what happens to the most extreme particles, because those are easy to find. But what happens to the bulk of the flow? Why does something heat up? Is kind of a difficult question to answer. But it's not impossible. We're still working on it. OK, so let me show you another example of these simulations where the plasma physics is important. This is a simulation of interaction of cosmic rays with the magnetic field in front of shocks. So in, say, supernova remnants, it is inferred that magnetic field is amplified to levels much larger than what would be inferred from just simple shock compression of the interstellar magnetic field. And what has been proposed is that if you have a shock, say, moving in a supernova remnant, and it's accelerating cosmic rays, so it's efficiently accelerating cosmic rays, then what you have is a cloud of protons going back and forth around the shock, and on fairly large scales. And that cloud of protons is moving together on average with the shock. So each proton is very relativistic, but on average, this whole cloud is being pushed by the shock. So that means that in the upstream medium, there is a current. There is a current of positive protons that's trying to propagate through the upstream. And that current turns out to be unstable to generation of a particular instability called non-resonant cosmic ray-driven instability proposed by Tony Bell in 2004. So the basic idea looks like this. So you have initially a background magnetic field. Initially, it was uniform. And the cosmic rays are trying to stream through this medium. They're trying to carry a current. That current will be compensated by electrons in the background plasma. And then, so initially, there is the net current is 0. But those background electrons are magnetized. They're feeling the magnetic field, whereas the cosmic rays are fairly energetic, and they move through with large Larmor radii. What you find is if you set up this initial configuration, again, there is a free energy here. If you set up this initial configuration, you find that it's unstable. And this is what it looks like. So initial straight magnetic field gets a wave on it. So this wave has a circular polarization. You can see here in the, maybe you can see, there is a transverse magnetic field shown in the slice. What you see that the vector of the magnetic field is rotating like this. And so this externally provided current of cosmic rays is driving the background plasma unstable, and it's driving, it looks like sort of an alpha wave, but except it has an opposite direction of polarization. And the growth rate and the wavelengths depend on the wavelengths depend on the current provided by the background particles. And what you find is that you can actually grow the magnetic field to levels larger than you start with, maybe by factors of 10. And then that field will get compressed at the shock. So this is probably reasonable instability to work in the environments of the supernova remnants. So here's an example of what it looks like in 3 dimensions. Initially, the field was uniform. And what you're seeing is that the field is wound up in these spirals. And these spirals are becoming nonlinear, and they're pushing the plasma apart. So what's shown here, the slices are density, and the white is the magnetic field lines traced from some predefined location. So as you can see, by the end, I can't trace very far. Some field lines just wander off. And what you find is that there is these loops filament the plasma, and ultimately those different plasma regions start to collide with each other, and that's what saturates the instability. So this is the example of what it looks like in 2 dimensions. So this is the magnetic energy, and this is the density going through the plasma. And what you find is if you run these simulations longer and longer, you go insane. So be careful when you're using large simulations. They start screaming at you. Okay, so yeah.
Supernova remnant. So how probable is it that the magnetic field will be along the vertical
Right, you're right. So what's important is a projection of the current on the magnetic field. So the instability works quite well for quasi-parallel configurations. So when you have magnetic field within some range of angles. We recently investigated what happens if you actually have a completely transverse magnetic field. And it turns out that a sister of this instability exists even in that case. It doesn't quite work in the same way, but basically it makes a transverse magnetic field filament like that. So it pulls, the cosmic rays try to pull the magnetic field forward, and they make fluctuations like this. They don't have the same polarization, but the growth rate and the ultimate saturation seem to be very similar to this Bell instability. So it seems to be robust in all configurations of the angle. Okay, so what have we learned? So far what I've shown you is the kind of shocks that you create in different environments. So this is the relativistic shocks and the non-relativistic shocks. What we find is that the instability, so the mediation mechanism for shocks depends on what kind of magnetic field you have in the background. If the magnetic field is weak, you're mediated by this Weibull instability or filamentation. If magnetic field is strong, you have a magnetic reflection of the shock. And different types of shocks produce different types of acceleration. So if you have a weakly magnetized shocks, then Fermi acceleration seems to be well established, especially in the relativistic case. This is the example where the self-generated field gives you the scattering. In the case of the magnetic shocks, the acceleration does work, but only for a particular set of angles of the magnetic field. So magnetic field has to be almost parallel to the direction of the flow in order to work. And recently we've been interested in exploring this for the non-relativistic shocks. And I can show you a few slides on that. Let me just skip this. Right, so non-relativistic shocks are intrinsically more difficult. The main reason is that not everything is moving at c anymore. What all scales were the same when you had the thermal velocity equals to speed of light, when you had motion velocity equal to the speed of light. Now, for a non-relativistic shock, they're all different. And that introduces different scales that you have to be careful that you're resolving or not forgetting about. And so far, we've been able to push these simulations to almost realistic parameters. So we've done mass ratios up to 1,000, and we can lower the velocity of the flow down to about 3,000 kilometers per second. So this is now in the range of the supernova remnant parameters. And the difficulty here is that, if you want to simulate something moving at 3,000 kilometers per second, that's 1% of the speed of light. Your code has to resolve the speed of light because this is a fully electromagnetic code. So you're wasting a lot of time steps trying to simulate something very, very slow. Yet, if you have a large enough computer, you can do it. And here is a typical example of a mass ratio of 400 Mach number 5 shock. So this is 18,000 kilometers per second. What's shown here is the density. This is the density through the domain, integrated through the box. This is a two-dimensional simulation. And this is the momentum space. So what you see here, this is the incoming protons. They're reflected at the shock, and then there are particles going back towards the upstream. And this is the two-dimensional density and two-dimensional magnetic energy, two-dimensional magnetic field out of plane. So what you see is that there are certain waves that are generated in this region where particles are reflected. This is what's known as a shock foot. This is an overshoot in the shock. So there's a lot of nomenclature from the geophysical shocks around the Earth magnetosphere. But all of this seems to happen. And also what we can measure is the temperature of electrons and ions. So what you see here is this is the ion temperature, and this is the electron temperature. So the electrons warmed up quite significantly while going through the shock. And this warming is essentially due to plasma physics that happens in this interaction region between the returning particles and incoming particles. So this is a fairly low Mach number. This is a higher Mach number. You can see the filamentation starts to set in, but then it gets overwhelmed by magnetic compression. So this is kind of a marginal case. It's not quite filamented, not quite magnetic reflection. And finally, this is a Mach number 140, which is a typical Mach number range if you actually believe that the magnetic field is not amplified in supernova remnants. If you just take the ISM magnetic field, then the shock does form, but it takes its time, and it's essentially filamentary. So you can see the filamentation and the creation of magnetic filaments is what's driving the shock. Okay. Sorry, what? This? Okay, so right. So what you're seeing here is the initial particles that were reflected off the wall. And that's not a shock. This is just a simple jump by a factor of 2. A shock happens when this jump actually extends to larger than a factor of 2. So this is where the shock actually is. You can see in phase space, this is just two beams going at each other. But here they started to isotropize. So they're actually starting appearing particles with zero velocity. Okay, so there are additional applications of these types of methods to pulsar magnetospheres, which I will not have time to talk about. They're also quite interesting to me. There's also applications to reconnection, and I will not be able to do much justice to reconnection here, but all I'm going to show you is a simulation from Bill Doughton, where you're seeing the density in the reconnection region, and the magnetic field is coming in like this into the reconnection region. What you see here is reconnection happening here, and the jets of material flying out in the reconnection region. And using these simulations, you're actually resolving both ion scales and electron scales, and you can measure the reconnection rate and find how fast is fast reconnection. And what's being done right now, and you will hear more about it on Thursday, hopefully, from Kevin Bowers, is simulations on the largest supercomputer in the world, this Roadrunner in Los Alamos, where three-dimensional reconnection problem was attempted and actually succeeded in a fairly large box, I think 100 by 100 by 100 ion skin depths, if not more, and actually 200 ion skin depths on the side. And what's shown here is a three-dimensional current sheet, which is in the transverse cut, seems to be undergoing some sort of three-dimensional instability. It kinks around, and that greatly increases the rate of reconnection in 3 dimensions. Okay, so to summarize my talk is we have finally I've discussed two of the typical types of simulations of plasmas, the electrostatic and electromagnetic method. The electrostatic method is more or less understood by now. The electromagnetic method has different flavors. Different groups try different things and argue about which one is better. There are several formulations that work better for ultra-relativistic flows, like the simulation that we did. There are methods that work better for non-relativistic flows. There are some approximations you can make. But basically, most of the research now is trying to use these electromagnetic schemes. And in astrophysics, ab initio simulations seem to have the promise, at least, to address some fundamental theoretical questions, such as particle acceleration and the possibility of having two temperature plasmas and how dissipation of turbulence happens and how reconnection works. So let's see. Right, so the results that I showed you give the evidence for ab initio particle acceleration. So you can actually create a collisionless shock in the computer and see it accelerate particles without any initial assumptions. And with this, we can actually address what kind of conditions you need for particle acceleration. And that can put constraints on what kind of scenarios you can have, like whether magnetic fields can be strong in astrophysical outflows, whether they can be transfers to the flow, and so forth. We now can study the influence of cosmic rays onto the amplification of the magnetic field and cosmic ray feedback on the structure of the shocks. And I haven't talked about pulsars, they're fun, but finally this long-standing problem of reconnection and calculating the rate of reconnection and the physics of the reconnection region is being addressed with three-dimensional simulations on largest computers. So I'll stop here. If you have any questions, I'm going to be around. Thanks.